address some questions, and I have kind of an agenda of some items I want to cover to make sure that, it's quite possible you may see some questions about them on the exam. Zachary, did you have a comment?
Oh, well, I wasn't sure how this review was actually going to go.
Okay.
So I was going to ask, and I'm not sure if it's really a good question at all. You said that each of the tests will be, everybody's test will be different?
The actual items you get will be different, yes.
Oh. Well, could you, just tell us, exactly what topics that everyone will need to know?
Well, everybody needs to know everything in this. The questions that cover exactly the same material. The questions are just different.
Oh, okay. Well,
yeah. We're going to go over a little bit so that you have an idea what you need to be studying. But pretty much, it's everything on the syllabus up to this point. And we'll cover some key things that you probably haven't reviewed in a while during the review tonight.
Okay.
What I would like to do first is, does anybody have any specific areas they'd like for me to go over? If you do, pop your microphone on and let me get it on my list here. Last night's class only had 4 things that they wanted, and then I reviewed about 15 things on top of that. Does anybody have anything in particular that you'd really like for me to go over at least one problem of?
Circuit problems, if possible, please.
Oh, what type, Tatiana?
Circuit.
Like a circuit, like with a transistor, that type of thing?
Mm-hmm.
I can't understand you. Your microphone's breaking up.
Oh, yes, that kind of thing. Sorry.
Okay, so I'll put a list
Yeah, I
here.
could use a review on that too.
Okay, that's good. All right, transistor down.
Code point to surrogate.
What's that?
The code point to surrogate.
Ah, yes. Good points. Okay, we'll definitely do a review of that because that's been a long time since we did that. And some of that's, it's not hard. It's a lot of steps. And you kind of have to remember then. On the exam, one of the key things to remember is you're probably going to have exactly enough time to finish the exam if you don't spend all your time looking through notes to figure out what the answer is. So you want to be prepared, and you want to, if you have to go to the notes, know exactly where something is that you need to look up. If you wrote down everything that I've been saying since the semester started, you'd have, 1,000 pages, and you'd never find anything in it. So you need to, as part of your study this weekend, you need to make sure that you organize what you do have, and that you then, if you need to dig into it, you're able to. Somebody asked class, what was it, open book, whatever? Yeah, it's open book, totally open book. I can't monitor what you're actually doing. I'm going to put you on your honor not to be talking to other people. You can't have some expert computer scientist sitting in the room with you and talking to them, or even contacting other people in the class about a particular question. Because while the questions are different, there may be similar questions on the exams. And while you're rooting around trying to find somebody else that has a question similar, you'll be burning up time that you need to be actually working on the exam. So the way it works is the same as we did that one exercise in class one night. I'll give you a secret number. Won't be very secret. I'll tell everybody what everybody's number is. But you will then fetch that particular copy of the test, and then you'll work it. Your answers will go inside the angle brackets that sit in front of the question number. And you can also put other notes and things on that same file. Like if you want to prove that you had worked a problem or something, you might show some of the steps up to getting the answer on that page. You don't have to, but sometimes people like to, when they see it later again, they'd like to know what they were thinking. And so I'm going to be looking inside those angle brackets at the answers, and the file needs to be a text file, a .txt file. It can't be any Microsoft Word or any pretty printed RTF files or anything like that. It's got to be, a text file. And it shouldn't be difficult. Just make sure you follow the directions very carefully. If something asks for you to give me an answer back with 2 significant digits, don't give me 3. Don't give me 1. Give me 2. Something says it wants an answer in hex, don't give me it in binary, give it to me in hex. If a question is says, give me the result of your calculation. That means don't do any rounding, don't do anything. Give me what the calculator, and these are grocery store calculators, ultimately return to you inside the angle brackets. As we do a couple problems tonight, we'll make sure we do them in a way that we force an answer to, you scratch your head and say, I wonder how I was supposed to submit that. And then I'll tell you. One of the advantages of coming to the review session is, not that you're getting credit for being here, but that the fact that you were here will make you do better on the test ultimately. So, among the people here on the test are probably the only people that will get A's. The people that didn't come tonight for whatever reason. I mean, they may not be here for totally legitimate reasons. Maybe they have a job and work on Friday night. Maybe they haven't gotten home from New York City yet, type of thing. And there's nothing we can do about that because I only have a little bit of time available during the week that I can use. Office hours are still, the hour after class. And some of you have been making use of those to good advantage, I think. But, I couldn't review every test item with everybody because I can't really teach the class twice. I have to teach it once and then talk about questions you might have. So we're going to basically start with the website. It's over on the screen. And don't forget that this is here. This has some very important information in it that might be useful on a test, not so much to work the test, but to check your answers. The other place, and I can't show it to you because I don't have the same access to Blackboard that you have, is in the assignments area there where I have listed a bunch of files and notes and things like that that hopefully you've been downloading and taking the key ones and making printed copies so you don't have to keep looking them up if you're working on a problem. What we have over here, of course, item 1, what's useful here is the schedule, because the schedule shows us down through here the items that are going to be on the exam and that you need to brush up on over the weekend. What's missing here is multiplexers. We did multiplexers, I believe, the same night we did maybe counters and shift registers. No, it was before that. Digital components. We probably did them that night. And that's not on here. And let me look at my own schedule here. And the word LED doesn't appear on here anywhere, but it has diodes. That implies regular diodes as well as LEDs. Would be things you need to know about. So this is here for study. And during the exam, this isn't going to be real useful. But to make sure you've covered all those points, up to exam 1 would be key in your preparation. Now, the next thing is the powers of 2. Should you forget one, they're supposed to be memorized, but should you forget one, they're all here. Here's the one you memorized up through 16. So, you do have a place to go quickly if you need to be able to look one of those up. Maybe you forgot whether 2 to the 8th is 256 or 255. You can't remember what it is. Well, you should have it memorized, but if you don't, this is a fast way of finding it. The next item, which is our prefixes, is a very important one. Remember, we're always moving numbers so that there are multiples of 3 in terms of decimal point placement. And the main things we normally see with the small voltages and currents we're working with will be kilos when we're talking about resistors, or milli, micro, maybe nano and pico if we're talking about capacitors, but primarily milli and micro as our units. So let's say we had worked the problem. Let me see, I got a calculator somewhere, my grocery store calculator. And let's say that I had 9 volts and it was divided by 0.026 amps, which would be 260 milliamps. I get this number. And this is the answer to my question, my problem that I'm getting ready to respond to on the exam. If the test says it wants you, let me grab an old test. I don't have any new tests, but let me grab an old test here. If it says express your answer in decimal with 2 digits of significance, for example, which would be typical for us, the answer you'd be putting inside the brackets to that question would be 35. And I don't remember the problem we were working. I think we used volts and amps, and you'd be computing another value. So you'd have your units following it in there. And like I say, I don't remember the problem I just worked. But where does that page go? Here it is. So let's pretend like it was ohms. And you just put 35 ohms inside the brackets. This number rounds up to 35 because of the 6, and then we have our 2 digits. Remember that in any answer you have, let's say you got an answer in the calculator that looked like this. You always have to have at least one significant digit to the left of the decimal point. You could have 2 and you could have 3, but after that you're going to be in another prefix. So this number here, in order for this to be correct, is going to be written as 1.0, whatever units this thing is. Let's pretend like this is in volts. So when you write this out, you're going to write this out with the 1 in front of the decimal point, followed by the next section. So the answer here that you're actually responding with is millivolts. So if the answer you were asked to return, said give it to me in decimal and with 2 digits of significance, this would actually be the answer you would submit, and you'd put that answer inside the angle brackets that are provided to you. Oops, put the angle bracket in the wrong place. All right, this is what you had actually calculated. When you turned it in as an answer, this would be the right answer. This would be right, this would be wrong. So if you submitted this and this isn't the answer, we always justify our numbers so that there's either 1, 2, or 3 digits to the left of the decimal point, and generally it'll ask for 2 digits of significance. In this case, that would be these 2 digits right there. If this had been, 5 or 6, this would have been 1.1. Now I got the same problem, same keyboard tonight, where the keys have been moved one position on me. I think somebody thought that was a great spoof. So that would be the answer if this was the value we calculated. While we're doing these, let's calculate a couple problems. Let's say we had a voltage equal to 9, and you do these with me. We had a voltage of 9 volts and a resistance equal to 2.2 k ohms. Put the k ohms over here. I'm going to actually put spaces before my units to make them clearer. And the question we're being asked is, what is the current and what is the wattage, the power? So work those 2 problems, and then I'll work them with you, and we'll see how you would have done if those had been 2 test questions. And they very well might be. When you get the answer, just pop up a green circle for me. I'll wait till about a handful of you have got it done. It's very low-key tonight. I'm not tracking your answers or, checking your attendance or anything like that. We're trying to make sure you do well on the exam. Okay, let's remember our rule. We need Ohm's law, which is the voltage is equal to the current in amps times the resistance in ohms. So voltage in volts equals current in amps times resistance in ohms. We need the power formula, which says the power in watts is equal to the current in amps times the voltage in volts. So in the first case here, we know the voltage, we know the resistance. So what we need to do is get this guy isolated on one side by himself so we can divide both sides by R. So I is equal to V divided by R. So we take 9. We divide it by the resistance, which is 2,200. And that gives us back this number right here. So I, if we were putting this on the page in between the brackets here, would be 0.00409 milliamps. But we're going to move the decimal place so that there's a digit to the left, at least one, 2, or 3 digits to the left of the decimal point. So it's going to be, and in 2 significant digits, it's going to be 4.1 milliamps. If I get the arithmetic wrong, somebody correct me, because I'm doing it while you're doing it. If you hit the wrong keys on the calculator. 4.1 milliamps. Decimal point needs to be moved over 3, which would put it right after the 4. And since this first chunk is called milli, next chunk's called micro, right? But the milli, so we have 4 millis, point something, and the point something, if we need 2 significant digits, 9 would round to 0 up to 1. Now, in order to get the power, we're going to put it inside its little brackets. We need to take the voltage times the newfound current. Now, if we were working this as a change problem, I would not re-enter this number. If you have to re-enter it later, you'll re-enter it as 4.1 milliamps. I would simply use this exact number we have until we're done with the equation. And multiply this times 9 volts. That's going to give us a number that looks like this. We move the decimal point over 3 places. It's going to put 2 digits in front of the decimal point, so we have our 2 significant digits to the left of the decimal now. The 8 will round the 6 up to a 7, and then the answer to that will be 37 milliwatts. Anybody have any questions about that?
Not really over this problem, but just sort of your question in general. So, should we get an answer in micro units? Do we actually type in a U into the answer, or can we just type in, what do we type in for the answer?
Type in a lowercase u.
Lowercase u, okay.
It looks like a micro.
Okay.
Anybody have any other questions? Let's do a different variation of the same problem. Make sure we understand it. Let's say that we had a voltage which is unknown. We have a current equal to, let's use it, 123 milliamps. We have a resistance equal to 1 megohm. What we want to find out is what is V and how much power is being dissipated. Try to work that one. If you can set this equation up. I mean, there'll be a handful of these, I'm sure, on the exam somewhere, because even if you're solving a circuit problem, ultimately you have to work these, even if they're not presented as a question like this. Give me a green light when you get an answer there. Is it really just plug into the calculator? Okay, so we're going to set V equal to I times R. This has to be expressed in amps. This has to be expressed in ohms. So put in I. Will be point millis. Actually, it is millis. I have micros there. So point 1, 2, 3 amps times 1 meg is at 6 zeros. So times a million equals that number in volts. Okay. That's a lot of volts. How would we write that down as an answer? Well, first of all, think about the number with only two significant digits. It's going to be 1, 2, 0, 0, 0, 0, 0, 0. You only want significant digits, 1, 2, or 3 of them left of decimal points. We want to get rid of these 3. So to get rid of those 3, I need to put a K. So kilovolts. 120 kilovolts. We did the arithmetic right. Okay. Making sure I did the calculations right. Let me read into that because that's a big number. 0.1, 2, 3 times. Yeah, that's right. And so with the two significant digits, we don't do the two that we don't. Wattage, we would take and take our current and multiply it times the voltage. So I use the voltage I calculated, not the one that I put in the answer block. If I have to recalculate something, I'll use the one in the answer block. As long as I'm chaining equations together, I keep using the numbers that have significance. I'm going to multiply this number times the current, which is point 1, 2, 3. That's equal to 15,129 watts. So we want 15,000. We're going to have only two significant digits, and we're going to get rid of the 3 at the end and write K watts. You don't want to be anywhere near that, so I think you'd shock yourself like crazy.
Professor?
Yeah.
Volt is equal to 123 kilovolts, right?
Say it again, I can't understand you.
Voltage. Answer is 123 kilovolts, right?
The answer is 15.
No, not B.
V is 123, right? It's 123 plus 3 zeros. We rounded it off to the two significant digits.
Oh, okay.
Okay. But while we were doing the equations, see, we could still calculate power without ever having to stop the chain of equations we were entering. We would just leave the numbers we were getting because they provide it homes in on the answer a little better. But if I were now, somebody said, okay, calculate for me what half of this, if this were at half of the voltage, we just take 60 kilovolts as a half. We wouldn't take, 100 and whatever half of that would be, 63 and a half. Okay. So make sure you know how to put the answers in. Let's say we saw a question. We probably will. It said, how long does it take to discharge a 0.1 microfarad capacitor? And then it didn't say anything about significant digits, meaning that it wants a decimal number and it wants the actual computed value you get. How do we do this problem? Somebody jump on and tell me how we do this. Somebody should be objecting right now to the question.
We need a resistance, right?
Yeah, you're exactly right. We got to have it through what? It could take all day if we didn't have it hooked to anything, right? So through, let's say in this case we're going to be using, let's use a 3.3 k ohm. Now I can't write sigmas, big sigmas, so I'm going to have, or omegas, I mean, so I have to write the word ohm out when I do it. If we were using a circuit program or something, that would be the funny looking Greek capital omega. Now this we can answer. Who wants to give me the equation we're going to be solving?
Resistance times capacitance, I think it was.
Okay. So the resistance in ohms times the capacitance in farads will give us how long it takes to discharge to 37%. How long does it take to discharge all the way to 0? This is a time constant. How many time constants did we say we needed in order to either charge or discharge a capacitor? Always the same.
It's 5.
5, that's right, Joseph. Good. The times 5. So our resistance is 3,300. Let me clear this. Make sure I'm working with a fresh screen. 3,300 times. Now we need 0.1 microfarad. Let's work that out over here. 0.000, that's the millis, that's the micros, and that's the 0.1. So this is the answer of the value of that capacitor in farads, which is exactly what we need. You might remember if I hit the time sign yet? We'll see. And the answer we get is for one time cycle. If I ask you what the time constant is, you wouldn't have to do times 5. You'd simply give me this number, and this number would be represented in seconds. And how many seconds is that using our method of engineering notation?
330 microseconds.
That's exactly right. And so we're going to take this times 5. And this is our answer. Now, since the question didn't ask us to put it in 2 significant digits, we'll leave all the digits, but we'll nevertheless convert it to engineering notation. So what is this guy in engineering notation? What are we going to be putting inside of the brackets? Go ahead, Joseph.
That would be, shoot. No, I messed that up. Sorry.
Okay, yeah, you're doing pretty well with the answers you've been giving me. So this would be how many milliseconds? Well, 1, right? What's 1? Point. 2 microseconds hanging over, 65. And the first guy himself is in milliseconds. Usually use lowercase s for seconds. The answer would be 1.65 milliseconds. The decimal point would be shifted over 3 positions, which makes it milli. And then there's got some fractional stuff. If we'd been asked to put it with 2 significant digits, we'd round the 6 up to a 7, and this would be just 1.7 milliseconds. So you have to read the question carefully to make sure you see what is being asked of you. Anybody need to see any more of this type of math problem? So the next thing on our table here is the Ascii chart. Now, while it's handy to check your answers, I will propose to you that if you have to come here and look up all of the Ascii characters you're using, you're going to burn up more time than you have on the exam. So I would use this to check your answers, because your eyes can fly through this really quickly that way, but not to look up every detail of any question that uses Ascii characters. Memorize the key points. Space is a 20. 0 is a 30. Uppercase letters are always their number, like first letter added to 40. Lowercase letters or whatever letters, so J is the 10th letter, it'll be a 6A because it's 10 added to 6 with a 6 in front of it. Key points to remember: first letter is A, 10th letter is J, 13th letter is M, 16th is N, right? That's the middle of the alphabet. 20th letter is T. Of course, 26th letter is Z. You might go, well, there's a 10 next to it. Yeah, because it's 16 plus 10 is 26. So we added a 1 to this 40 to get the 5, and then we brought the 10 along with it. So these are really easy to compute in your head if you just remember those anchor points. So let's do an ASCII problem, because I'm sure there's going to be some of those on there. And remember, in all the questions we're doing, they could go either way. Meaning, I could give you some ASCII and ask you some questions about it, or I could give you some text and say, turn it into ASCII. Let's say somebody said, somebody took the word honk and said, write that out in ASCII using even parity. Here's some brackets to put it in. Go ahead and try to do that. And I've been timing that. You should be done with that with a question like that at that point. If you're still working on it, you're going to have to, get a little better at it. Okay, let's work this one together. Letter H, 2 letters before J, so it must be the 8th letter of the alphabet is uppercase, so it's 48. O, the letter after N was 14, so it must be 15. Lowercase, so it must be a 6F. N is the letter before that, so it must be 6E. It must be the 11th, it's JK, right? It's the letter after that, so it must be 6B. Now let's check those. This is where the other table comes in handy. Really quickly, we can look at 48 and see an H. We can look at 6F, 6E and C and N, and C and N. Sounds like a news station. 6B, we find the K. So that was quick. Now let's write it out in binary. Since we've memorized our nibbles, and then double check that I got it right, because I'm doing the same thing you would be doing, just pulling those out of my head. That's a 4, that's an 8, that's a 6, that's an F, that's a 6, that's an E, that's a 6, and that's a B. So I must have gotten it right. So what we're really doing here is we're taking, and I'm just going to drop these down on their own lines. I'm going to count the number ones, and if it's an even number, I don't have to change that bit. It's already even, already even. This is odd. There's 2 there and 3 there, so that's 5. So we need a 1 there. 3 there and 2 there, that's 5. We need 1 more. So now we would write it back out, because they probably want your answer in hex. It's 4, 8, 6, F, E, 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 B. We pick this number up. We pop it inside there, be done with it. Moving on. Now, if you used uppercase, be consistent. That's still right, but be consistent. Don't mix your upper and lower case. So if you had taken the original problem and written it down, these would have probably been written as uppercase. Any question about that? You might also be given one of these, and somebody might ask you, what is the characters, and is it even or odd parity? Or space or mark. Remember, space and mark parity. If it's mark parity, that means that every character has the top bit turned on. If it's space parity, it means that all the characters have the top bit turned off. Because even, the bit up here makes the number of bits in the byte be even. And if it's odd, the bit that goes up here is making the number become an odd number. Any questions about that? If you have them, this is a good time to ask them. I guarantee any question you have, 3 other people have the same question. They're just shy. Okay, let us move on then. If we've got ASCII under our belts. The next thing we encounter is Unicode. I would suggest to you this is a great page to have at your disposal. So I would keep that, the course web page, I would keep it near me at all times when I'm taking the test. A question you'll probably get along the way is, given code point, and then it's some number, let's say 1, 2, 3, 4, what is the name of that character? Put it in this box if it's the code point. Only code points go in here. Hit go. If there's a chart available, meaning it exists, because it could be a code that's valid but hasn't been assigned any characters. If, however, it's in the chart, it'll be in this section here. It's part of the Ethiopic language. We said 1, 2, 3, 4, so we go down the 1, 2, 3 column to the 4, which is right here. We admire it for a second. We realize that that's not what the teacher's asking. The teacher's asking for the name of that character. So in most of the code pages, you go down to the bottom, you can look up the number here. It should be down at the bottom of that column here. And it's the Ethiopic syllable C. I would simply highlight that, copy it, take it back over wherever the test has angle brackets asking me what the name is, and drop it in there. I wouldn't try to retype it or be creative or anything. I'll just pick it up out of this chart and drop it in. So if somebody asks you what code point 1, 2, 3, 4 was, that's the answer. Anybody have any question about that? Okay, what is the character 005F? That's a code point, 005F. You do it yourself. You're going to type 005F here. You get it? Give me a green light. This is fun tonight. I don't have to teach you anything. I can just review what we've done. Normally, if we were doing this session at school, we ought to have brought in some pizza. But you know what? We don't get to go to school anymore. We got to stay at home or in the office. I can stay in the office here all day. Okay. We did go. It would give us a code page. Turns out it's an ASCII character, but we don't want your guess at what it is. We're going to go down here to the bottom and literally look up 005F. To pass it by. We see that 005F is called a low line. And that would be the answer that would go in inside the parentheses here. Notice that a low line is also what we think of as an underscore. So if you put underscore, that would not match the answer key, so the machine would grade you wrong, because this is the answer of the code point. This is the answer in ASCII that it's probably called. It's also considered a spacing character, not to be confused with these characters, like a double low line, or something called a combining low line. This really takes and is used with other characters to kind of modify the way that character looks. So its actual name is low line. Any question about that? Let's now think about code points for a second. Put one up here. Let's say somebody gave me the code point. We take and make an easy one. 3, 4, 5, 6, 7. And they said, write out that code point in UTF. Remember, all the UTF things are ways of encoding that code point. So let's say somebody said, use UTF 32 big endian. And they want the answer in hex. This is already in hex if they say it's a Unicode code point. What would be the answer to that? This is the easiest question of the entire night. Anybody want to take a shot at it?
Hey, you said in hex?
Yeah, the answer in hex, because the code point's in hex.
674503.
That would be little endian.
Okay.
The big endian is simply going to be, it'll be 32 bits with that right justified in it. Now, we notice here that we're actually using, what, 18 bits. So we want to keep that in mind in a couple of minutes. The UTF 32 little endian would be 6, 7, 4, 5, 3, 0, 3. Did I get them right? 0, 3, 4, 5, 6, 7, 0, 0. We take a byte at a time and put them in the other order. And with 32 bits, we have to exchange all of the nibbles and bytes around like that. So this is the UTF-32 encoding of the same thing. Now you might get a number like that. Somebody might say, this is encoded in UTF-32 little endian. What's the code point? What would the code point actually be? Anybody want to take a shot at it? I guarantee you this question's on the exam with a different number.
Would it be 00003412?
Right, and we can get rid of the leading zeros, so it would be 3412. Just don't do like I did and delete the brackets when you're putting the answer down. So this would be the code point, and you'd write them all pressed together like that because it's 32 bits. Now, let's do another easy one real quick. Let's say we were using that code point we talked about a while ago, 1, 2, 3, 4, and somebody said, write that in UTF-16 big endian. How would you write that?
Just 1, 2, 3, 4. Right?
You got it.
Yep.
Maybe that's the easiest question of the night. That's even easier than the other one was. So if we took UTF-16 little endian, you'd have 3412. And we'd write all 16 bits together because they're a unit of 16. So if we had a second character, it would be separated with a space, and the next character would be like 4444 or something. So if you're writing in units of like 16 or 32, so when it's 32, we write all the 32 bits pressed together. When it's 16, we write them in a set of 16 together. So if a UTF-8, we're going to write single bytes when we get there. So we said this is 3412. And then we go back and we take our original code point, because it was one we loved. Now let me show you a little business here as well. I'm going to go put that number in as we're going to go check this out. I say go. It's going to come up to a screen that says this is not assigned. So if you were asked what that character is, here's what to copy. Code point 34567 is unassigned. Copy that. You put that in the angle brackets. That would be sufficient to tell me what the name of that code point was. You don't need any of the other stuff on this screen. But let's pretend like we want to encode it anyway, because we might. What's the first step to encoding a character? What's the first thing we do when we're doing, well, I got to tell you where we're putting it, right? We're going to put it in UTF-16 big endian. We're going to encode it. So what's the first thing we have to do?
Do we have to convert it to binary?
Well, we'll do that along the way, but there's one really kind of, I'm almost going to call it a naive step we have to do. We have to recognize that it's bigger than 16 bits. We've used up 16 bits here. We're in the nibble now that can take us up to 20 bits. So we're bigger than 16. We can't be encoded directly in UTF-16 because we're more than one unit of 16. So that's who gets to enter the room right now. Mr. Surrogate Pair and the Dancing Bear. Mr. Surrogate Pair gets to come in. So we know our ultimate answer is going to start somewhere in the range D800, with the first byte being no bigger than DBFF, and the second, or the first set of bits, the second one starting at DC00, going up to DFFF. So we know that's a given. If we ever see a character that's in this range, we know we're looking at the first 16 bits of a surrogate pair. If we ever see these in that range, we know we're looking at the second 16 bits of a surrogate pair. So got some work to do. We got to get this number crammed into this. So first thing we're going to do, and you may not remember this step, but it's a very important one. We're going to subtract from it what looks like 10,000. Anybody remember that? Give me a green light if you remembered that. Yeah, sure, you remembered that. No, of course you did. You guys are brilliant. You're my best class this year, other than maybe my other one. Well, maybe you guys are equal this time. I haven't decided yet, till after the first test. So what are we going to do? We're going to subtract what looks like 10,000 from that. We're going to get 2, 4, 5, 6, 7. Now, who was it a sec? Was it Nick that said, do we get to put this into binary soon? So let's put it in binary. 2, 4, 5, 6, 7. Okay. Now, how many bytes, how many nibbles did we write out there when we did that? We wrote 5. We need to split it in the middle, right there, so that we have 10 bits in each portion. The first 10 bits are going to be right justified and added to our high surrogate. The second part is going to get right shifted and then added to our low surrogate. So to do that, first thing I'm going to do is I'm going to get rid of the spaces and then reorder it so it is in normal nibbles and stick a couple zeros on the front of this so it also is 4 bits long. Now it turns out that if I'm going to add this to something that is 4 nibbles long, I need 4 more zeros as well. All I've really done is I have taken and I've created 16 bits, and I've right justified the 10 that were to the left, the 10 that were to the right-hand part of the word we had here, and then the other set we put here. So now this thing right here, oops. Okay. That thing needs to be added to D800, which is in hex. So what's D800 in hex? It's D800. We can add that up. It's 1101, 1000, 1001, 0001. We just added that up. The next one's going to be added to D Charlie 00. That's going to be that stuff. So let's write D Charlie 00. We got D Charlie 00. Let's add that up. 1101, 1101, 0110, 0111. So this line here we care about, and this line here we care about. Let's rewrite this guy now in hexadecimal. Looks like he's a D891. And this guy down here looks like he is a DD67. What is it? Yeah, that's right, 7. And if I just put him on the same line, I have my surrogate pairs. So, surrogate pairs and the dancing bears have all worked that problem, and there's our answer. We took this number, we subtracted out what is officially at the 17th bit, that 1-bit position. Then we rewrote our number into binary. We split it so that there were 10 bits left and right of center, because this right in the middle of the 5 is a split. Then we right justified those two sets of 10 bits, and we extended them to the left with 0, so each of these is 16 bits long. Then we took the first one and added it to D800, which made our first high surrogate. And then we took the second one and added it to DC00, which gave us our low surrogate. So this is the encoding of that number in UTF-16 Big Endian. Anybody have any questions about that? Or do they need to see another example?
So
in the angle bracket, you go first. Okay. So in the angle brackets, we would just write D891 space DD67.
That would be the answer right there. Mm-hmm.
Okay.
Yes, sir. And somebody else was talking?
Yeah. To go back from this surrogate to the code point, you would just reverse all of the steps.
Let's do that. Let's actually take a different one. So let's say we get a piece of code and it said, I don't know, 23 D 49. Actually, I want this to be lower. Make this be D9. 49 D. And somebody said to us, oh, I know what that is. That's a UTF-16 encoding in Little Endian of some code point. What is that code point? Why don't you see if you can work around, just to see if you can even write out what the steps would be in order to do that. First thing we know is it's going to be more than 16 bits in the answer because we're using a surrogate pair. Otherwise, we would have just encoded it in a single 16-bit entity. But see if you can figure out what the steps would be. See if you remember the most common forgotten step? Don't worry if you don't work through the answer right now. I'm not going to probably give you enough time to do that, but make sure you know what the steps would be. At least figure out what it is you need to do. Okay, how we doing? Anybody want to tell me what the first step is?
We would have to convert that to UTF-16 big endian first, right?
You wouldn't have to, but ultimately we have to. Let's do it now, just like you said. So what am I going to write down?
D923. DD49.
Absolutely. Now I would check at this step to make sure that this number is between D8 and DB. And I would check that this number is between DC and DF. Because if it's not, there's something invalid going on. This number has to be between D800 and DBFF. This number has to be between DC00 and DFFF. And this passes muster. It's perfectly okay. So the next thing we do is we think about what did we actually do earlier to get this? Well, we had added the first one to D800. Remember doing that? So we could actually right here subtract D800 from this. We could subtract DC00 from that. So if we did that, I mean, this is just looks like even simple arithmetic. Even though it's base 16, we could most certainly do that. Start on the right. 3 minus 0 is a 3. 2 minus 0 is a 2. 9 minus 8, a 1. D minus D is a 0. Okay. Over here, 9 minus 0 is a 9. 4 minus 0 is a 4. D minus C is a 1. D minus D is a 0. And we could have done that in bits. I mean, you could have. It just looked pretty easy to me to do just in hex right there. Since we're supposed to know how to do hex arithmetic, that seems like a reasonable thing to do. So now I would suggest writing them out in binary. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. That's the first one. And let's put the second one below it. 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1. Y'all double check me. Did I get those right? Somebody give me a green light if I got it right. Thank you, Alexander. Okay, so what do we need to do here? Well, this is that thing we padded to make 20 bits out of, and by adding 6 zeros at the beginning. Let's just remove those 6 zeros. Okay, so this is the 10 bits we had. And if we recall, we got that 10 bits because they were actually hooked together like that. So let's get rid of the spaces and regroup. So we need 4 in the end. 4, 4, 4, 4, and 4. We have 1, 2, 3, 4. There's 16 bits. We knew we needed some more bits over here to the left. Let's write those out in hex. We have 4, 8, D, 4, 9. Now, most commonly forgotten step. What is it?
You have to add 10,000.
Right, we have to put back the 10,000 we took out earlier. So the code point we ultimately get is 58D49. This would be the answer that you'd put if somebody asked you what the code point was. Everybody reasonably okay with that? Thanks, Joseph. Thanks, Zachary. Thanks, Alexander. Thanks, Nicholas. Okay, we got a bunch of people that are becoming comfortable with this. Does anybody else need to see anything else having to do with surrogate pairs? Okay, one more type of Unicode we need to worry about, UTF-8. These are bytes, and remember they're the compressed values. So let's just take that last value we created here, and let's figure out how we would write that in UTF-8. I'm going to write it out again in bits. I get it right? You'll check my math. Otherwise, you'll copy down something's wrong and you'll swear it was right. I assure you I will have made at least one arithmetic mistake somewhere during this tonight. Okay, I'm assuming that means I got it right. So to do UTF-8, remember there are three types of, three generic types. If you have an X, 0 and 7 bits, basically that's how you store ASCII characters in UTF-8. If you have a byte that starts with 2 1s and a 0, and there'd be 5 more bits, that means I'm starting a 2-byte sequence to store the character. The continuation byte always starts 1 0 and can always contain 6 bits. The most this can store is 11 bits. If I started with 3 1s and a 0, I can only store 4 bits here. I still have this, which can store 6 bits, but I can have one more of them. So 6 and 6 is 12, 13, 14, 15, 16. So in that, I can store 16 bits. So if this starts 1, 1, 1, 0, I can only store 3 bits here, but now I get 3 of these things. Store bits in. So I have 6, 6, 6. That sounds demonic. I have 18, 19, 20, 21. So I can store 21 bits, which is the biggest Unicode character. You never need more than 21 bits. So ours needs from the 1 to here. 16 bits is here, 17, 18, 19. We need 19 bits, so we're going to have to be fit into this last state. So I'm going to take this. Remember, the leading 0 doesn't have to be stored. It probably will be, but it doesn't need to be. And then what I'm going to do is I'm going to start pushing things over until they line up with X's. Now, when I do that, I'm going to notice I didn't make it all the way to the right. So what that means is I really needed to do that from the right toward the left and then fill it with zeros as I go along. So I'm going to have to push these over one more. This guy right here actually belongs with that group. Those 6 go with that group. And that 0 over there winds up here. Now we're missing a 0 at the beginning of this. And we can literally bring down the leading business. Since all these are continuation bytes, they all start out the same. Now we can encode each of those bytes. The first one is an F1. The second one is a 9-8. The next one is a B5. The next one is an 8-9. And since they're byte oriented, the encoding is stored as bytes. They would be separated by spaces. And now we've taken this number here and we've encoded it into UTF-8. Use this final compression scheme. Anybody have any other questions about that? We also could maybe have to do it backwards as well. We could give you, this, and you'd have to work backwards to get to the actual character. But I think that's easy enough to just even think in your head how you would do that. Notice there's no big indent or little indent associated with UTF-8. It's always single bytes. Any questions about Unicode? Any other questions? We're going to move on if not. No questions? Okay. I'm counting on all A's out of you people, let me tell you. Earlier, we had a 2.2 k ohm resistor. What is the color code? If it is 1/2 watt and 10% tolerance. And you're going to put an answer inside those quotes. These are actually always going to be at the start of the line, but I'm just throwing them in now just so we remember to do it. Never in the code do you write one of these, however. Make sure you, like I'm using them for arrows here, don't you put them in because the machine that grades does first cut for your grade will get lost and make your entire test have to be mechanically graded, and you don't want that. You want it to be automatic. So how would we find out what the color code is? We got something on this page that helps, which is this, of course. So how would we encode a 2.2 k ohm, 1/2 watt, 10% resistor? Somebody take a shot at it.
Would it be red, orange, silver?
And of course, when you wrote it in, you do it that way. What's the red? It's a 2. Second red is a 2. How many zeros are there in 2.2 k ohm?
Thousand.
Well, let's write this number out as it actually would look. It would be 2,200. Okay. Red, red, orange would be 2, 2, and 3 zeros.
So then would it be red, red, red?
You got it. Red, 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 because we only have 2 zeros in the number. It's a little hard to, with the decimal point in there, you actually have to write it out and look at the number and say, what am I encoding? Because we're always encoding it in ohms. We're never encoding it in kiloohms. So this extra point in here shifted this out of one of the main positions it would be in, which means it ate up one of those positions in the K. Okay, so you could use this chart if you had to. What happened to the half watt? Where did we encode that?
I thought wattage didn't like go on there. It's only on the packaging.
That's right, and that's correct. So if somebody asks you what the wattage was, you go, I don't know. Idea, you know. So we can do these. I don't think resistors are that tough to do. What about color codes for a resist or for a capacitor? If somebody said I have a capacitor and I want to represent two, let's use a different number. Let's use 33 microfarad. How would I encode that? What's its color code? Okay, trick question. Capacitor, resistor. We wouldn't use this chart anyway. Plus, capacitors don't generally have color codes. I didn't teach you the markings that are on them, but that's not the way they'd be indicated. We know we can't use this chart because all the multipliers make the number bigger, and microfarads is much smaller than 1 unit. So capacitors are normally dealt with in either picofarads or picofarads generally in the United States. And so they actually, the 1 with no multiplier usually means 1 picofarad. But we don't use color codes for those. So a question that would ask you that would be a trick question, and it probably, well, I guarantee it wouldn't appear on this test because there are no trick questions. Everything I ask you has a legitimate answer. At least so far. I guess I could write one if you want one, but I don't think it will. Okay, so let's look at it. What's the next thing in our list of many things here? Whoa, that page is huge. The burger's looking pretty good. Standard resistor values. You finish working a transistor problem, and the thing says that you need a, let me pick one that's going to be, you need a 36.5 kiloohm resistor. What are you actually going to go get?
You said 36.5, but you put 36.6.
Yeah, I knew what the next digit was. I'll pretend like I don't. So what would I come over here and buy?
A 39 ohm resistor.
Well, 39 makes for a good choice here because it's a little bigger than 36 and is about the same distance 33 is from it, right? However, 5% there is a 36. So I could buy a 5% resistor of the right value. Now in real life, even though I could get this, I might specify it to be either a 33 or a 39 because both of those are available also as 10% values. And if I were prototyping something, I want to make sure when I go to the store, I can actually get it. I don't have to go back. So 36 might be one of those numbers that are a little harder to get. Where more of an issue will come in is when you're halfway between this. Let's say I got 41. 41 falls halfway between the 39 and the 43. So either one would work. But down here, you'll see the 43 doesn't exist. So the 39 would be a better choice. So just some designing rule of thumbs. You try to get the one that's closest to it, and if possible, is available in both 5 and 10%. Unless you hit smack on like we did here, in which case, let's go for it until we're told otherwise. And a question would not make that ambiguous. It would tell you which one you needed to pick. You would be able to figure it out. In this case, what's the color code of a 36.5 k ohm resistor? Anybody want to take a shot at it? Do I need to put the color codes back up? Well, the fact of the matter is that although we needed 36.5 and 36 was available, we have to throw that away because all resistors are only 2 digits of significance if we're using this chart. So we need a 3, a 6, and 3 zeros. We need an orange for the 3. What do we need for the 6?
Blue.
Blue. And we have 3 zeros.
Orange.
Orange. And we saw that the 36 resistor is only available in 5%, so we need a 5% band, which is
Gold.
gold. So we get an orange, blue, orange, gold. And then when we got it home, what is the range of values it might actually have? What's it, if we for a 36 k ohm resistor? Oh man. And what's plus and minus 5%? What's 5% of 36,000? 36 times, what I'm going to multiply it times? 0.05. Right? That's 5%?
Yep.
Well, think about it for a second. If I had 100 as my resistor, where's my clear here? What do I have to multiply that by to get 10%? B times 0.1. We were looking to get the number 10, right? So it makes sense that if I had 100, I could multiply it times 0.05, get 5%, because the number 5 comes out. So just as a quick review for you, we want to use 0.05 when we want 5%. So we have 36,000. I'm going to multiply that times 0.05. So we're going to have a 1800 spread. So if we take that number, we add it to 36,000. A resistor could be as much as 37,800 is the actual value. Or it could be 36,000 minus our 1,800, 34,200. So let's stick a comma in there. So our nominal value is 36,000 right in the middle. But our resistor could be a resistance this high, or it could be that low. Which one of these values lets through the most current? Do we care about when it's bigger or when it's smaller? Well, for testing things like current and power, we always use the smallest value the resistor could be. That's for current power tests. So if I were testing my circuit to make sure that my LED wasn't going to burn up, I would use that lower value. The other value is used to make sure you have enough juice. If this doesn't let through enough current, your light might not even be on. But we have to look at the whole range of the values to be able to make sure that the resistor we picked would be safe. Remember that in our calculations, we had actually calculated a value which was 36,500. Which actually I know when we calculated because I rounded it a while ago and somebody caught me. It was actually 490, 500. So the value we actually wanted in our circuit was this. So it's going to tend to have, plenty of current, even if it goes lower, that'll be bright, but we might also be forcing this guy higher in terms of current. So we want to look very carefully that we didn't exceed our values for our LED. Some general questions. How much voltage drops across a diode if it's forward biased? Somebody give me the number.
Isn't it
0.7.
0.7 volts, that's correct. How much voltage drops across an LED if it's forward biased?
2.1.
2.1 volts unless I tell you otherwise. Okay. We will come back to some details about that. Maybe we might be there already. Let me look and see. Nope, we're at floating point. Okay. First of all, let's say somebody gave us the number 0.1101100, and let's put a couple of other numbers up there with it. They said we want the 2's complement of that value. How do we create the 2's complement? Somebody give me the procedure.
You swap the zeros of ones and ones of zeros, and then you add a 1 onto the end, right?
Okay, that sounds correct.
Or yeah.
Okay, so we will do that. We'll swap all the bits. Piece on there. Now, we have to add 1 to it. So let me put a row above it so we can mark our carries. So 1 and 1 is equal to 0, carry the 1. 1 and 1 and 0 is equal to 0, carry the 1. 1 and 1 and 0 is equal to 0, whoops, not a 9, 0, carry the 1. 1, 0, 0 is equal to a 1, and it'll have a 0 carry. And everything else, this will be a 0. And all of this stuff right here will just basically pass through because there'll be no carries. So the 2's complement to this number right here is 11000010, and then 1000. So this answer here is the negative version of that. Had we been given this, we could figure out what its positive was by just simply doing the same operation in the other direction. I gave you a second way of doing it. One of my students figured out, which is always go to the last one and leave it alone, and everything that follows. He says, go to the last one, leave everything else alone, and then swap everything else that's above it. If you look at the row of what he did, Mr. Coakley, and that row, they match. We have a way to check your answer. You can use the Coakley method, or you can use the strict 2's complement. You know, flip all the bits and add 1. You ever hear the term 1's complement? 1 complement means flip all the bits. It doesn't include the add 1 part. It's called a 2's complement when that happens. Let's say somebody asks us to take the decimal number 74 and a quarter. Let's actually make it 0.75 and write that into fixed point binary. Remember, don't you ever write one of those arrow characters, either forward or backwards. What do I do? How do I do this? The number's in decimal. We need to have a binary and then turn it into hexadecimal answer. So I'll just put over here so we would know to do it. Answer in hex. What's the first thing I have to do? Anybody want to take a shot at it? No? The first thing I would do, if I were asked this problem, I'd write out 74 and 3/4 like that. I want to make sure that this fraction is over some power of 2. Because if I gave you a problem like 74 and a third, you have no idea how to do that. I didn't teach you how to do that. We only know how to do the ones that have some fraction which is a value over a power of 2. So I'd make sure of that first. Next thing I'd want to do is convert 74 into binary. Right, that makes sense. Bunch of ways to do that, but let's do an easy way. 74 minus the biggest power of 2 that's less than 74. What is that number?
64.
64, which leaves us with 10 minus the biggest power of 2 that's less than 10. Somebody else answer that.
8.
Okay. And we're going to subtract. That's going to give us the number 2 when we're done, right? Then we're going to subtract from that the biggest power of 2 that is less than 8 or less than 2, which is somebody else.
1.
I can get a bigger one. Bigger. It can be less than or equal.
Up to.
Okay, which gives us a 0. Okay, so we need the 64-bit, the 8-bit, and the 2-bit. Since we memorized our positions and powers of 2, we know that's the 128. That'd be 64, 32, 16, 8, 4, 2, 1. We now have the number 74. We can test that also because it would be, this is the number 4 times 16, which is 64, plus 10. That's 10. That would add up to 74. So this is the number 74. And then what we need to do is we need to take care of the fraction part. Point. The fractional part is 3/4. Well, in 3/4, we have a half. And we have a fourth. That's 3/4, right? We need to make this 4 nibbles long, or 4 bits long, so we'll add 2 more zeros just to lengthen it out. So that means we can write down the number 4 A point Charlie. And we have succeeded in writing that in hex in fixed point binary. Any questions about that? Okay, let's now take the same number and convert it IEEE 754 single precision, floating point. That was fixed point, we need floating point. So we need 3 pieces of information. We need enough to be able to create a sign bit. We need something to be able to create an exponent. And we need to be able to create the mantissa or characteristic. Sign is easy, right? Is this a positive or a negative number? It's positive. So the sign is going to be encoded as a 0. The exponent is a little trickier, but we know that if we don't shift the decimal point at all, it's going to be relative to 127. So let's figure out how many positions we need to shift the decimal point in this number. What we have to do is we have to shift it left or right until there's only a single 1 right to the left of it. So we have to go 1, 2, 3, 4, 5, 6 positions. Just make a note of that. We have to go plus 6 positions. And then just so we don't forget it later, everything to the right of that 1 is the mantissa. Except for it won't have that decimal point in it. And no spaces for now. Okay, so here's our exponent. It's 127. We have to add 6 to it. We could do that, or 127 plus 6 equals what? 133? Or if we wanted to, if we had the number 128, we could add 5 to that and still get 133. So I'm much happier with 128 because it's this. And to add 5 to it, it's as simple as that. So the number I got right here is the same as 6 plus 127, or 5 plus 128. We can check that. 127 plus 4 is 132, plus 1 is 133. I think we got everything we need. Grab the 0, grab the exponent, grab the mantissa, and start breaking it up into chunks of 4. We need add a 0 to this guy. And we have 1, 2, 3, 4, 5. We need 6, 7, 8. We need 8 nibbles. Now we can write those out. 4, 2, 9, 5, 8, 0, 0, 0. And now we have created the IEEE 754 single precision floating point encoding of the number 74.75. Anybody have any questions about that? Now, you might actually be given this and have to work backwards. Does anybody need to see that happen? You can just basically read this in the other direction, but we can do it. Let's put another number down here and just give it a shot. Let's say the number we have is a 408223334. So what would be my first step? Think about it, we're going backwards up this list. I'm going to write it in binary. Okay. So now I have written it in binary. This thing was gotten by putting the parts together. Sign bit, the exponent, and then any remaining bits that we had, and then putting zeros on the end of it. We can now break this back into its component parts. That's a 0. Oops. This guy needs to be regrouped a bit here. And we'll pull him over. And then all this stuff, we'll just get rid of the spaces, and then we'll deal with it later. Okay. So what is this number right now? This number is 128 plus 1. That equals 129, which when minus 127 is equal to 2 positions, right? So we're going to have to, when we take our answer, inflate it by 2 to the 2. So the decimal place will move 2 positions from where we originally put it. Okay, that being said, we're ready to do some work. This guy is the Mantissa. If we remove the normalization part of him, we're really going to stick a 1 in front of it, right? That's the one, the hidden 1. Now we need to move that decimal 2 points to the right. I'll get rid of that, move it to here. Now, assuming I did my arithmetic right, which I may or may not have, the number now that's to the left of the decimal point is the number 4. So we're going to have 4 point something. What is the something? Well, it's this big horrible thing here. Because now we're in fixed point, right? We've unnormalized the number. We know that we don't have any halves, quarters, eighths. We have a 16th. I'll write that down so I remember it. Maybe. I think I'd eventually get this on the screen if I pulled on it. So we have a 16th in the answer. 32nd, 64th, 128th, 256th. Five 12, 10 24, 20 48, 40 96. And so forth. I'm not going to finish the rest, but as you can see, these are contributing less and less and less and less and less to the number. So this is approximately 4 1/16. there's some additional stuff out here to make it more precise, but 4 1/16 will, the example we're working right now. And of course, if we wanted to make it a decimal number, we could just come over here and say, well, 1 divided by 16 is equal to 0.0625. So 4.0625. But the teacher told us that we wanted to have it in 2 significant digits, so it's really equal to 4.1 when we're done. Yeah, probably on an IEEE number would not ask you to do that last step. I'd probably have you leave it as it is. And of course, if the answer was not that we get with the answer in decimal here, but if we were told to put the answer in hex, that's easy at this point, right? We make sure we got 1, 2, 1, 2, well, we would just make sure we have sets of 4. 4.1119A would be the 6-point answer in hexadecimal. And that's working the problem backwards, which I'm sure any of you could do. I just have to think about the steps probably a little longer than I do because I've done them before. Okay, any other questions about anything having to do with floating point? I remember gave you the standard here for single precision. Not that you need it for the test, but if you did need it for the test all of a sudden, this will tell you how many bits there are and where. And down here, there's a little table that's kind of nice. It says if the exponent is 0 and the fraction is 0, you have basically the number 0, right? If the fraction is not 0, you have what's called a subnormal or denormaled or denormalized or dirty 0, sometimes it's called, which means it's a fraction piece, doesn't have that 1 hidden, and whatever number you get is times 10 to the minus 120, 2 raised to the minus 126. So that's a special case. If the exponent is anything from 1 to FE, you're just going to see, regardless of the 0 fraction part, it's just going to be that thing we've been doing all semester. Otherwise, you might have infinity, and infinity could plus and minus just like 0 could. And if you did have something in the fraction part instead of zeros, it's not infinity, it's what's called not a number. And you might have to know something about that. So it's easy to find a little table that's sitting right in the middle of that one link right off of our homepage. If we do a, what are they called, state machine, I posted Terry's excitation tables so they're really quick to get to. You don't have to go fighting through a bunch of paper looking for them. And chances are pretty good you'll have to do a state machine. But I'm not going to review those tonight particularly because we've just been doing those the last couple of lectures, and so they should be fresh in your mind. We have a couple other things to do first. We might get to one. Not so sure. Does anybody need to see a Carnell map problem? Anybody need to see a Quinn-McCluskey problem?
Sure, let's do one of those.
Okay. Well, let's do one that we'll do actually both, Quinn-McCluskey and a Carnell problem, just to make it more lively. Because I know there's probably people that haven't completely figured out how to do them. Okay, we're going to have, let's say, ABC and creating a Y. And one of these lines, I think it was this one I left the space off of. Okay, so let's take a truth table and let's take 1, 0, 1, 1, 1, 1, 0, like that. Good enough. And first of all, let's do the Carnell mapping of the thing to try to get the equation. And then we can, anything with, 3, 4, 5 things, you probably want to check yourself by using both Quinn-McCluskey and Carnell on it. So let me see if I got one laying around over here somewhere. I do. Let's build ourselves a fancy little Carnell map here. What's the name of the top row? What am I going to write here? A, B, C, not A, Q. What am I going to write in front of this?
Not A.
Which means this guy will be A. Somebody else answer and tell me what the name of this first column is.
Not BC.
Not B, C?
Not B, not B, not A.
Not B, not C? B?
Yeah.
Not C.
Not C.
Okay. This would be not B, C. This would be B, C. And this would be B, not C. Okay, so let's kind of map this. 1, 0, 1, 1. 1, 0, 1, 1. 1, 1, 0, 1. 1, 1, 0, 1. Okay, so a couple ways we could do this, but a fairly straightforward way to do it would be to grab those, grab those, grab those. Now we wouldn't want to grab this one, because if we did, it's completely contained inside of those two. Wouldn't want this one for the same reason. However, we could have grouped them differently to start with. I mean, another perfectly legit thing to do would be to group those two together, those two together, and those two together. And none of them, they'd all have the same number of terms and they're equivalent. We'll go with this one. The answer for this would be Y is equal to the name of the first column, which is not B, not C. These guys are going to have an A in their name because they're on that row. And then what doesn't change? Well, C doesn't change, so C is in their name. Or up here, we're in the not A row. And B doesn't change. So we quickly have an equation for that. So let's check our work. Now, we may get one of the other answers when we do our Quinn-McCluskey, but we can come back and then verify that we could have drawn those circles. So let's put out to the side here that we're going to have a zero group, meaning there's no bits turned on. We'll probably have a group that has one bit turned on. Some group that has, I don't know, let me put it over here, 2 turned on. Let me undo that. Oops. We'll have some groups that has 3 of them turned on. Let's go. Do we have a place where we have a 1 and there's 0 group, or 0 input? Yeah, there's no 1s. So we put 0, 0, 0 over here. In the 1 group, we've got 0, 1, 0. We have 1, 0, 0. And then in the 2 group, we have 0, 1, 1. And 1, 0, 1, right? And then in the group of 3, let me put an extra space line in here so that they don't run into each other. We have 1, 1, 1. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I get the right, did I fill that out right? This is the 3s. Double check me. Okay, so what we're going to do is we're going to compare what's in this against what's here. And if there's only a single bit matching, we're going to create another entry in a column over here to represent that combination. So this compared with that will be 0x0. This, and actually I'm going to put a little z over here to mean check mark. They've been used. 0 against this guy will be, excuse me, x0, 0. So he got used. Now we've got to start with this group and compare them against this group. So this guy compares against him as 0, 1x. So he gets a z. That's a check mark. He will not successfully compare against the next guy because too many bits change. This guy compares against him very nicely, 1, 0x. So he can get checked off. And we're through with that group. So he compares to him as x11. Which means he's going to get checked off. And he compares against him as 1x1. Did I make any mistakes? Okay, I'll assume your silence is that I made none. Now we're going to compare everything in this group against this group, and this group against that group. We only need to compare if the x's match. So he doesn't matter. There's nowhere in this group that has a center x. So no, he's done. He can't get checked off. Same thing here. He can't get checked off. This guy has to compare with the x's match, but they don't match in either case, so they can't get checked off. And of course, they don't compare against anything. So we're done. We have our answers. So now we need to build the table of choice. Across the top, we're going to put all the things that need to be covered. You know what? Let me just write this in text, and you all use your imagination here. We're going to cover 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1. Did I get them all? I think I did. And we're going to list our prime implicants as the row indicator. So first prime implicant is this guy, then this guy, then this. So we're going to take all of these guys in turn, and we're going to list them on a separate row. So we have 0x0, x00, 0, 1x, 10x, x11, and then 1x1. Everybody agrees with that? These are the prime implicants, and we're looking for the essential primes. So what we need to do first of all now is we have to mark which ones are covered. Let's see if I can do this in a scientific way. Oops. Okay, this guy covers anything that starts and ends with a 0, which would be him. That's it. This guy covers anybody that ends in 2 zeros. That's him and him. Get the right row for him? I don't think I did. I did not. Yeah, I did. This guy covers anybody that starts 0, 1. That's him and him. He covers anybody that's 1, 0. That's him and him. He covers 0, 1, 1 if we've got it. Or 1, 1, 1 if we've got it, which we do. And he's got 1, 0, 1, and 1, 1, 1. Let's see if I'm on the right row there.
I think you might have made a mistake.
I might have.
Doesn't 0x0, doesn't 0, 1, 0, wouldn't that count?
Did I miss it?
There's no...
Oops. Teach me to push the control key instead of the shift key. There we go. Where is it? Moved. Okay, so we got good coverage. Remember, we're looking for the ones that are absolutely necessary. And for them to be absolutely necessary, there would only be one X in the column. So now we've got some choices to make. We have to take and pick values that cover everything. So what I'm going to do is I'm going to pick this guy right here and say that these two terms are covered. So he's covered. Let's make them lowercase z's. So they're covered by him. Now, I don't want to cover any, I want somebody that's unique for coverage here. And so, let's see what else we have here. This guy is unique. So let's keep him. So now we've covered that. Now, we must have made a mistake somewhere in our typing, I'm thinking. Because, why don't I put 2 Z's there? We know that, and you'll have to go back and check if I did. We know that not B, not C, which does turn out to be this guy, right, is included. We know that not AB, well, AC is concluded. That's this guy. So the first thing, but not AB is supposed to cover the rest of them. And he doesn't appear to. So we've made some sort of a mistake up here transposing things across. I'm not going to go that. I got another thing we need to cover first. Does anybody see it right away? Very likely happened when I was putting the X's into the table.
Sure, I got the same. The X things I got the same.
You match me.
But the only difference was that I have the 0, 1, 1 and 1, 0, 0 swapped, but that shouldn't matter. I got 0x0, 1, 0x, x1, 1.
Mm-hmm.
That seems to work.
Okay. So the problem we have right here is if I take any two, if I have an overlap like this, I shouldn't, let's see, maybe this guy. I don't want to spend a lot of time trying to do this, but let's just back check what we did. 0x0, x0, 0, and here we got an x1, a 0, 1x, 1, 0x, an x1, 1, and a 1x1. Did I write my numbers down correctly?
Yeah, actually, yeah. So the first row
Uh-huh.
and the fourth and fifth rows should cover everything.
Well, yeah, ultimately we want this. We want the last row. And we wrote down over here, maybe we wrote it down wrong over here.
Yeah, because I didn't use the last row. I used let's see, 0x0, 10x, x11.
We use this guy.
Yeah. That should give full coverage.
Okay. So let's see what we did over here then, because that should also cover. Well, and this is a good practice item. We need to have not A, not C. Oh, that's what the problem is. This was not a guy I wanted to use. So I'm probably leading us up to an extra term with that. So not BC is the second row. AC is the bottom row. And I'm going to undo this for a second. Not AB is this guy. Now, does that cover everything? That still doesn't cover
What's
this.
weird is that for me, not A, not C, or A, not B, or
Mhm.
B, C. That's what I got as my final equation.
Here. Say it again.
Not A, not C,
Uh-huh.
or A, not B,
Yeah.
or BC. And that should be not C at the first one.
Right here, not A, not C.
Yeah. Yeah.
Okay, so let's cover those. I'll use green again. We have not A, which is this row, not C, which would be this. We have A, not B, which would be these two. And we have BC, which are those two, which does cover it as well. But it should have worked additionally. We should have been able to extract my case out of it also. And so somewhere I've typed something wrong over here. And literally I don't want to push it, so I'll let you figure it out on your own. His solution works, so we'll go with it. If you pick the cases he did, which were the not A, not C, A, not B, or BC, we see it does cover everything that our other one covered. That would convince me to check the Carnell problem again, because we got a different answer over here when we tried to use my answer. So his is probably right, and something in mine is typed wrong. Well, that'll give you something to try to figure out. It'll give you a challenge. Because the red squares, or red circles, should work as well. Because each of them is a set of two. They do complete coverage, and there's no overlaps anywhere. Which means there has to be at least three things over here, which cover two of them, and two of them. And he found one of the sets that do that. So good job. Real good job. Okay, let's move on because we're going to run out of time if we don't. Let me scroll this up. Let me get rid of this. And color one is black. Okay, so what I want to do now is I want to look at if we had an equation in a truth table that looked like, let me see, truth table, where I got one there. I think I got one there. And we were told that we need to design this using a multiplexer with 3 address lines. Meaning that our multiplexer has only 3 inputs. And then it has 8 data lines. Y pops out over here. We know these are A, B, and C. What should we hook to those lines? See if you can figure it out, and then we'll talk about it. Okay, anybody want to volunteer a solution for what the first one should be hooked to? Remember, this line is addressed when A, B, and C are 0, 0, 0. You use the multiplexer, which means it's going to route whatever's hooked to this out to Y. So we want to have the 0 come out if we have 0, 0, 0, 0. But remember, we have D not as an input down here. So what am I going to hook? Remember these lines, the second one 0, 0, 0, 1. The last one is 1, 1, 1. As you recall, if we divide these into sets of 2, then the multiplexer is going to take A, B, and C, which happen to be the same, and make the output be strictly dependent on D. So what the output looks like here, it's a 0 no matter what D does. So we can hook a 0 to that wire. What would we hook to the second wire? Second address. Anybody can answer.
You would hook a 1.
That is correct. Somebody else answer and tell me what's hooked to the third one, the one that's 010. This guy right here.
Would that be a 0?
Well, it looks like when D is a 0, we get a 1. When D is a 1, we get a 0. So we can't hook a 0 to it because we get a different answer depending on what D is.
Not D?
Not D. That's exactly right. It's going to be just exactly the opposite of what D is. The next one, which is at 0, 1, 1, will be this. Notice how it matches D exactly? So it would be D. And so forth. This one would be a 1. This would be a 0. This would be a 1. This would be a not D. And we simply use D as part of the inputs because it's always going to create either a 0 always, a 1 always, exactly D, or exactly the inverse of D. And so we can use those 4 things to hook to it and then pick which one we want by setting A, B, and C to pick the pair. The pair is picked by the first 3. Anybody have any questions about that?
So how would we input something like this as an answer on a test?
Chances
What
are
would we put in the angle brackets?
Well, it would depend on exactly the question. Let me see what the question that has had this in, or a question from a previous exam would have said. I haven't written this one yet, so that's why I can't tell you right away. I think I asked for an equation. But let's see. The answer for this would be D0 equals 0. Because the top line's actual name is D0. Space D1 is equal to 1. D2 is equal to not D. D3 is equal to D. D4. You get the idea? Goes back eventually.
Yeah, that makes sense.
For each of the Ds, unfortunately, we have D2 places. This chip has, D0 at the top and D7 at the bottom. If it were a 4-input one, it would be D0 to D3. If it was a 16-input one, it would be D0 to D15. What do you think these are actually called? We're calling them A, B, and C in terms of the signal, but what's the name of those on a multiplexer? This is A2, A1, and A0. It's the address lines, and they're in order from high to low, whereas these are from low to high. If you turn this thing sideways, if we were to rotate it, you'd see that be on your right-hand side. That was a good question, by the way. I probably would have forgotten, but the question I'm looking at here is fairly clear if you understand all the other things. If I ask for an equation, you're just going to put the equation in. Try to put it without spaces. Use a vertical or an exclamation point to mean invert. Use parentheses liberally if necessary, but no angle brackets. And put spaces between the independent answers. Okay, let's talk transistors for a second here. And I want to use this page. Okay, I'm going to make some statements about a transistor, which actually answer a whole lot of the other questions I ask you about them. So these are some things that you need to just know. There's an arrowhead here, right, coming out. This is called Q. The top one is called the collector. The bottom one is called the emitter. The one over here is called the base. Anytime you see a voltage, if I say something like VBE, I mean, what's the voltage of the base with respect to the emitter? VCE, what's the voltage of the collector with respect to the emitter? There's really about 3 different things that a transistor could be doing at any given moment if we don't hook it up backwards. And I won't be hooking it up backwards in anything you all say. One of them is the transistor could be what's called cut off, meaning it's not running right now, it's turned off. It could be active, which means it's acting like an amplifier. It could be the way we've been using it mostly, although some of those chips that we looked at the insides of were actually using them as active. It could be saturated. I'm just going to write sat. Now, how would we detect these states? Well, one of the states, in terms of cutoff, would be if you were told there is no current going through the base emitter diode. Or there's 2 diodes in here, base emitter and base collector. But if there's no current flowing, it's cut off. Another thing would be if there's no current flowing through the transistor itself, it's cut off. In either of those 2 states, what we're going to see is we're going to see a much larger, I'm just going to put much greater voltage here relative to here. So if you see 10 volts here and the power supply is 10 volts, you can suspect that it's possibly cut off. It might be active, but it's probably cut off. The way you confirm that is you do not find 0.7 volts here. So the easiest place to look, if you can, is look to see that there's no 0.7 on VBE. That's an indication the transistor is turned off. Now, you will also, if it's cut off, see a large voltage. But you'll also possibly see a large voltage if it's active. So that's not the distinguishing thing for that. Now, if you do see 0.7, it's either active or saturated. So 0.7 means it's active or saturated. If it's saturated, VCE will be 0.7 volts or less. When we do problems, we actually estimate it to be 0 volts as an estimate. That's the voltage between here and here. If it's less than 0.7 volts, we're saturated. If you have 0.7 volts between the base emitter. Now, if we have 0.7 volts here and we have something greater than 0.7 volts, we are active. What active means is we're amplifying. And when we are amplifying, greater than 0.7 here, we'll find 0.7 there. Then and only then can we take IC and multiply it times beta, IB, and multiply it times beta to get IC. So only when we're acting as an amplifier can we do that. And we know that because we forced B to be too big in order to saturate the transistor. We forced it so that if you took the base current times beta, it came out much bigger than the collector current we needed. That's how we saturated the transistor. However, if we ever have the conditions that there's 0.7 across the base emitter, and the voltage from collector to emitter is greater than 0.7 volts, then it's true that whatever the current in the base multiplied times beta is, that'll give us the collector current. We're most likely to get a problem that says things like, there's 2 volts, what happened to my thing here? There's 2 volts on VCE. You will work a problem that then has a resistor of some value, a battery, and a resistor, a diode, and a battery, and you'll determine that you do have 0.7 on VBE. The problem will then ask you, using the current you just determined and the collector current you just determined, what is beta? This can only be calculated if you're in the active region. You can't calculate it if you're saturated. You can't calculate it if you're cut off. In this case, we would simply take whatever IC is, divide it by IB, and we would have had to determine what they are by just working the circuit problem. Now, let's assume, for example, I found out that I have 100 milliamps for IC. And I have 200 microamps for IB. I'm asked what beta is. I see that I have 2 volts across VCE, so I know I'm in saturation. I'm sorry, I know I'm in the active region, not saturation. I know I'm not cut off, which means I literally am in the active region because I have 0.7 here. I can now do the math because that's the only time I can calculate beta. I would take 100 milliamps to 0.1000, and the extra zero doesn't matter. I would divide it by IB, which is 200 micro, which is 0.0002, and I'd find out my beta was equal to 500. Remember, beta is unitless. And it says that while in the active region, anything going into the base will be amplified 500 times and will be the current in the collector emitter. Once we're saturated, remember how we got saturation? We took the current here, we divided it by beta, then doubled it to force it to be too much. There's no way we could get that current over here because the resistor was limiting it. And that caused saturation, which means we have less than 0.7 across the collector emitter. Okay, let's look at our syllabus and see if we got everything covered. Number system, ASCII, Unicode, resistors, Ohm's law, circuits, yeah, binary. We didn't do any arithmetic. Yeah, we kind of did. Deuce complement, fixed point, binary, diodes, LEDs, floating point standard, transistors. Get some combinational logic. You would need to rework, well, we'll talk about that down here. Boolean algebra. We talked a lot about that. We actually did a problem with Carnot maps, transistor circuits, digital logic reduction. We did that with Carnot maps, Quinn McCloskey. You need to rework my work, although the work that, who did that? Somebody turn your mic on so I know who it was.
Yeah, that was me,
Okay.
Alexander.
So, yeah. You want to check to see why mine didn't come out to the same answer. It should have. I made a mistake somewhere. We did not specifically go over the digital components. I don't know if you guys can hear me, but we got disconnected. I don't know if I'm going to reconnect. I know they're doing some maintenance tonight, so that might have happened to us.
I can
We
hear
can
you.
hear you now.
I can hear you.
Can you guys hear me?
Yeah.
Yes.
Okay. I'm kind of back. Let me see if I can reshare that screen. Maybe. No, I can't share the screen right now. But it looks like we talked a little about charge and discharge capacitors. The counters, shift registers, you've got handouts for that. State machines were so recent as was the FPGA and VHDL stuff. I think that's a pretty good review. You guys feel comfortable that you, with a little study, you'll be ready to make your A on Monday night?
I feel more comfortable. So
Yeah, I think you guys will do pretty well because I'm getting a lot of feedback when you do answer that shows you know kind of what's going on. Okay, I should be back. Does anybody have any questions that we would need to discuss?
just real quick for that beta problem again. If the problem were set up differently and we needed to find something else, what did you say we should assume beta is? Was it 200?
I'm getting a terrible echo off you, Nick.
Oh, sorry. Hold on.
I think 100.
Oh, was it 100? Okay.
What are we talking
Beta.
about?
Beta should be assumed.
Oh, in that
100.
last problem, it was 500 was the actual beta we computed. If you're doing your own problem, you assume 100. If
All right,
you're working a transistor problem, you assume beta to be 100. You assume that the BE will be 0.7. You assume the VCE will be 0 volts. And the drop across the LED is 2.1 volts unless you're told otherwise. And you want to plan for between 15 and 25 milliamps, with 20 milliamps being a good, design value. Did I cover all those? Is that everything?
I think
Yeah.
so.
Okay, and in case you didn't hear it, you do need to rework my Quinn McCluskey stuff just to see what in the world he did. Crazy teacher. And that'll be good practice for you anyway. Most of what we did was in the right spirit, although the answer didn't match. So I think that if you kind of looked at what we did and you did it again, you'd get the right answer anyway. And some of you did anyway, because that Carnell map was a very, I should say the equation is actually a really good one because you can make 2 or 3 different solutions to it, and they're all valid. And because they all have the same number of terms, 3 terms, each of 2 items ANDed. Okay, well, unless anybody has any other questions, you all have a nice weekend, and I'll see you right at 6 o'clock, and be on time if you can, because I'll be giving out some instructions at that point on Monday night. So have a nice weekend.
See you next week, Professor. Thank you.
Thanks,
Bye-bye.
you too.
Thank you.
Thanks, Professor.
Bye-bye.